In this work, we propose object-centric kinodynamic planning for nonprehensile robot rearrangement manipulation. Rearrangement-based manipulation is a class of problems where the robot is tasked to reconfigure multiple objects through interaction to achieve certain task goals. The figure at the bottom shows one example of such problems. By rearranging the movable cubes in different colors, the robot needs to relocate them to their corresponding goal regions. Traditional methods use only a pick-and-place type of prehensile action. The robot can manipulate only one object at a time by grasping it and placing it at a desired location. However, grasping objects can be infeasible when they are tightly packed and there is no free space around them, such as in a configuration shown by the left figure. More recently, non-prehensile actions such as pushing have been incorporated to allow concurrent manipulation of multiple objects. As shown in the bottom videos, various manipulation tasks can be achieved through non-prehensile action-based rearrangement, such as object singulation for grasping, relocating a target object, and separating objects into different clusters. Although the interactions between the robot and objects become more complex, non-prehensile actions have shown potentials to generate more diverse and efficient rearrangement solutions. Traditional non-prehensile rearrangement planners are mostly robot-centric, meaning that the robot actions are sampled only with robot-relevant kinematic and geometric constraints. When sampling a robot action, no consideration is given to how the object states will be affected by this action, and the outcome of the action is predicted after the sampling. In the bottom video, for example, by constraining the gripper's movement parallel to the workspace, a kinodynamic planner keeps sampling robot actions from explored states. The outcome state of each sampled action is predicted by the physics engine. By evaluating the predicted outcomes, the actions that complete the task or make the most progress will be selected for execution. Although the task is successfully completed, the selected actions are not effective enough because the action generated is not sufficiently guided by how the object should be reconfigured. In this work, with an object-centric planning paradigm, we propose the OCP rearrangement planner. Unlike the robot-centric paradigm, object-centric planning first reasons about how the object should be moved by assuming the objects can actively move without the robot. Then, the robot executes to realize the desired object motions through a pushing strategy. Each time, only one object is activated to explore its motion, and the other object can be passively moved due to interactions between objects. The activated object can move along a randomly sampled straight line for local exploration under Mode 1, or directly move towards its goal location by following an optimal trajectory under Mode 2. With both exploration modes, different object motions are sufficiently sampled. The sequence of desired object motions are then extracted to be realized by the real robot execution, which can contain both the straight line Mode 1 motion and the goal-oriented Mode 2 motion. After each real execution, the real-world object states will be observed for replanning. By interleaving the object-centric planning and real-world execution to close the loop, our OCP planner is able to progressively rearrange objects to their desired configurations. Under the object-centric planning paradigm, each robot action is generated with a specific purpose of manipulating certain objects, and therefore the solution plan becomes more effective. To evaluate our OCP planner on various rearrangement tasks, we conducted extensive experiments both in simulation with a floating gripper and on a physical robot. In simulation, when goal configurations for each object is not explicitly given, our OCP planner is able to efficiently sort objects of different classes into different clusters. In 6 different test cases with different numbers of classes and objects, we showed that our OCP planner can generate effective actions to succeed in all of the test cases. On various other rearrangement tasks with given object goals, we showed that our OCP planner is generally effective to meet different manipulation requirements. For example, the separate task requires precise local relocation of each object, and sorting 100 objects needs more global reconfiguration of objects. Our OCP planner can efficiently solve both the local rearrangement and large-scale problems. Then, on a Franca Emica Panda robot, we evaluated our OCP planner with more realistic challenges. For sorting objects without given goal regions, our OCP planner always succeeded within the time budget. As shown by the selected trial on the top, for 3 selected baselines, although they could still finish the task, It generally required significantly more runtime. When the number of classes and objects increased, our OCP planner still always succeeded with a similar speed. However, other baselines may fail the task when time exceeds the budget and object clusters are not far enough apart. For a large-scale setup sorting 32 objects with goal regions, our OCP planner still always succeeded within the time budget, whereas the other baselines could not finish the task within the 30-minute time budget for execution. Without object-centric planning, a lot of generated actions by the baselines did not effectively interact with the objects. Qualitatively, we showed that our OCP planner can rearrange objects in different shapes rather than just cubes. With letter-shaped objects, our OCP planner rearranged them to form the abbreviation TRO. Moreover, our OCP planner can also rearrange objects in different sizes, including both convex and non-convex objects. Finally, we propose a real-world benchmarking protocol to standardize and facilitate future research in non-prehensile rearrangement. The protocol includes 5 different scenes with different packing factors. The first 3 scenes are identical to the real-world evaluations mentioned before. The rest of the 2 scenes, shown at the bottom, require relocating each object to different classes to one of the corresponding goal positions. We would like to acknowledge our funding sources and thank you very much for watching.